Hello viewers, today I am going to talk about the second part of the crystal field theory. So here we will discuss about crystal field splitting in tetrahedral complexes. So as we see the diagrams, the splitting is somewhat opposite to that of the octahedral field, because in case of tetrahedral the ligands are in between the axes, the ligands are approaching in almost in between the axes. Therefore there will be the repulsion will be more in case of dxy, dyz and dzx, and hence it will experience a high energies, and the orbital which are in along the axis, they are experiencing somewhat less amount of energies, less amount of repulsion, so their energy becomes less. Okay, now if we see the octahedral versus tetrahedral splitting, crystal field splitting. In case of tetrahedral, the splitting energy is somewhat less than that of the octahedral crystal field splitting, and if we see the tetrahedral crystal field splitting is equal to 4/9 of that of the octahedral crystal field splitting. Because why? In case of tetrahedral there will be 4 ligands, and in case of octahedral there will be 6 ligands, right? The ligands field is roughly 2/3 of that of the octahedral field. Moreover, the direction of approach of tetrahedral complexes does not coincide with the d orbitals. So if we see the tetrahedral shape, tetrahedral structure, so the ligands are actually not exactly in between the axis, so it is somewhat near to the near to dx, xy, dyz and dzx. Okay, so therefore the delta t, that means tetrahedral crystal field splitting will be 2/3 into 2/3 is equal to 4/9 that of the octahedral crystal field splitting. And another thing you should know, why we write it as T2 and why we write as E instead of T2Z and EEZ, because the molecule in tetrahedral geometry, it is not symmetric, therefore we cannot write Z, Garade. Now if we see the crystal field stabilization energy of tetrahedral complexes, how we can calculate? So this is formula is that minus 0.6x plus 0.4y delta t plus np. It is np means how many number of pairs of pairing energy is there. If it is one pair, there is 1p. If it is two pair is there, so we write 2p. And x is the number of electrons in x is the number of electrons in e orbitals, and y is the number of electrons in T2 orbitals. Now we can calculate different CFSE for different configurations, D1, D2, D3, etc. And D1 and D2 it will be only one configurations, and accordingly we can calculate the crystal field stabilization energies by using the formula. Now for D3 there will be two possibilities. Okay, one it will be E2 T1 and another will be E3, and for this we can calculate the CFSE, and as it here E3 there will be a pairing, one pair of electron is there, so we write plus p. Similarly for D4 there will be two possibilities, and accordingly we can write the calculate the crystal field stabilization energies. Now this is the table through which we can see the crystal field stabilization energy for different configurations, okay, and high spin complexes. So D1, D1, D2, this is one possibilities. D3, D4, D5, D5 it is 0. Okay, and so on from D6, D7, D8, all we can calculate the crystal field stabilization energies.